NASA just found something strange inside Jupiter's Great Red Spot. Roughly 400 million miles from where you are sitting, there is a storm that has been spinning without stopping for at least 190 years. It is wider than the Earth. Nothing holds it up. There is no ground underneath it, no coastline to break it, no continent to drag against. It just turns, and turns, and it has been turning since before the invention of the photograph. And for 3 centuries, we assumed it was thin, a bruise on the surface, a pattern in the clouds. Then a spacecraft called Juno flew directly over it, twice, and measured the pull of its mass. And the storm turned out to have roots. It reaches down at least 150 miles below the cloud tops. Not across, down. Nobody expected the Great Red Spot to be doing anything like this. Stick around, because I'm about to walk you through what scientists actually confirmed about the inside of that storm. And hit subscribe now, because this channel breaks down real space discoveries without the exaggeration. Let's go back to where this story actually begins. In 1831, in the small German town of Dessau, a 41-year-old pharmacist named Samuel Heinrich Schwabe was doing something that nobody had asked him to do. Schwabe ran an apothecary shop. He sold remedies. He kept ledgers. His actual scientific ambition was almost comically tedious. He wanted to catch a hidden planet crossing in front of the sun, so he spent years staring at the solar disk, sketching every dark blemish he could see, day after day, for decades. He never found the planet. He accidentally discovered the 11-year sunspot cycle instead. But in 1831, he turned his telescope toward Jupiter, and he drew something else, a pale oval, sitting in the planet's southern hemisphere. That drawing is the anchor point. Everything astronomers say about the age of the Great Red Spot is measured from Schwabe's sketch, because from 1831 onward, the observations are continuous. Somebody, somewhere, has been watching that oval every year since. There is an older ghost in the record. In 1665, Giovanni Cassini and others described what they called the permanent spot on Jupiter. It was tracked until about 1713. Then, the observations stop, and there is a gap of more than a century before Schwabe's oval appears. So there are 2 honest possibilities, and researchers still cannot fully settle between them. Either the Great Red Spot is the same storm Cassini saw, making it more than 350 years old, or Cassini's spot died, and a new one formed in the same latitude band, making the current storm closer to 200. Recent modeling work has leaned toward the second answer. But lean toward is not the same as proved. For the next 180 years after Schwabe, we watched it the only way we could, from the outside. First through telescopes, hand-drawn, then photographed. Then, finally, up close. Pioneer 10 and Pioneer 11 passed through the Jupiter system in the early 1970s and returned the first spacecraft images of the spot. Grainy, low resolution, but real. In 1979, Voyager 1 and Voyager 2 flew past and did something nobody had managed before. They took enough sequential images to build a time-lapse. For the first time, humans watched the Great Red Spot rotate. It turns counterclockwise, completing a full rotation in about 4 to 6 days, and the cloud bands around it flow past in opposite directions, like traffic on either side of a median. Then Galileo, which arrived in 1995 and spent 8 years in orbit, mapping the cloud structure and dropping a probe into the atmosphere elsewhere on the planet. Every one of those missions gave us the same category of information: detail, color, motion, temperature at the top. All of it from above. None of it answered the simplest question a child would ask. How deep does it go? Because you cannot see depth. Jupiter has no surface to measure from. The cloud tops are just the altitude where the atmosphere becomes opaque to visible light. Below that line, everything is inference. And for 3 centuries, the honest answer to how deep the Great Red Spot went was that nobody had any idea, and no instrument existed that could tell you. The turning point came on August 5, 2011, when NASA launched Juno. Juno was not built to take pretty pictures. It was built to weigh things. Its entire purpose was to fly closer to Jupiter than anything had ever flown, and to feel the planet's interior through gravity. It arrived on July 4, 2016, and in February 2019, and again in July 2019, mission planners did something they had never done before. They aimed the spacecraft directly over the Great Red Spot. Here is how you measure the inside of a storm you cannot touch. Mass pulls. Every kilogram of gas inside that vortex tugs on anything passing overhead. Juno passes overhead at enormous speed. If the storm's mass is arranged differently from the gas around it, Juno speeds up or slows down by a tiny, tiny amount as it crosses. Those speed changes do not simply vanish. They show up in the radio signal. Juno is in constant contact with Earth through radio waves. When the spacecraft accelerates toward us, the frequency of that signal compresses. When it slows, the frequency stretches. This is the Doppler effect, the same reason a siren changes pitch as it passes you. The Deep Space Network measures that frequency shift with a precision that is hard to hold in your head. It can detect changes in Juno's velocity down to a fraction of a millimeter per second. That is slower than a hair grows. So the chain is this. The storm has mass. The mass tugs. The tug changes Juno's speed by a hair's width per second. The speed change bends the radio frequency. The frequency shift is caught on Earth. And from that shift, you can calculate how much gas is stacked up beneath the visible cloud tops, and therefore how far down the storm goes. Juno had a second instrument doing the same job a different way. The microwave radiometer, or MWR, has 6 antennas tuned to 6 different wavelengths. Longer wavelengths escape from deeper inside the atmosphere. So each channel is effectively a different depth. Stack the 6 readings, and you get a rough vertical slice. 2 completely independent methods. One measuring mass, one measuring heat. Both pointed at the same oval. That matters more than it sounds. A single measurement of something this strange is a claim. 2 measurements, using unrelated physics, arriving at compatible answers, is evidence. Gravity does not care about temperature. Microwaves do not care about mass. If they agree, the agreement is not an artifact of one instrument's quirks, and there is a detail in the orbital design that most coverage skips entirely. Juno does not orbit Jupiter in a circle. It follows a long, highly elongated path that swings far out beyond the worst of the radiation belts, then dives in steeply, skimming just a few thousand kilometers above the cloud tops, then climbs back out. The dive is the measurement. Everything else is the weight. That shape was chosen deliberately, to keep the spacecraft out of the radiation as much as possible. It also means the useful data from an entire 2-month orbit is collected in a window of minutes. And on those 2 passes in 2019, the mission team had to time the dive so that the storm, which is moving because Jupiter rotates once every 10 hours, happened to be underneath the spacecraft at the exact instant it swept through. Now understand what it cost to get those 2 passes. Jupiter has the most violent radiation environment of any planet in the solar system. Its magnetic field accelerates electrons to nearly the speed of light and traps them in belts around the planet. Ordinary electronics do not survive there. Juno's brain sits inside a titanium vault weighing roughly 400 pounds, built for one job: to keep the radiation out long enough for the spacecraft to finish counting. Juno runs on sunlight, not plutonium. Sunlight. 3 solar arrays, each about 9 meters long, spread out like blades. At Earth, those panels would generate something like 14,000 watts. At Jupiter, 5 times farther from the Sun, they deliver roughly 500 watts. 500 watts. That is less power than a household hairdryer. That is the entire energy budget of a spacecraft, measuring the interior of the largest planet in the solar system. At closest approach, Juno is moving at something near 130,000 miles per hour. It is the fastest any human object has traveled relative to a planet. The whole pass, the part that matters, the part directly over the storm, is over in a matter of minutes, and then it has to leave. Juno's orbit at the time of those measurements was a long looping ellipse that took 53 days to complete. 53 days between attempts. Get it wrong, and you wait almost 2 months for the next chance. There is no repair option. Depending on where the 2 planets are, a radio command takes somewhere between about 35 and 50 minutes to cross the distance one way. By the time you notice a problem, the moment is already an hour gone. By the time your fix arrives, it is 2. So nothing can be flown live. Every Peri-Jove pass is written in advance, uploaded as a script, and executed by a spacecraft that is entirely alone while it happens. Mission Control does not watch the pass. Mission Control finds out how the pass went. Afterward, once the data crawls home. And there is one more constraint that gets left out of almost every summary. Radiation damage accumulates. Every dive through the belts degrades the electronics a little more. Juno's camera, its star trackers, its detectors, all of them have measurably deteriorated over the mission, which means the spacecraft was always working against a clock that only runs one direction. The best data Juno would ever take was, by definition, near the beginning. The gravity passes over the Great Red Spot happened roughly 2.5 years into a mission that was originally planned to last about 20 months of science. 500 watts, 53 days, 150 miles down. Hold on to those numbers. The result was published in Science in 2021, led by Marzia Parisi at NASA's Jet Propulsion Laboratory, with the gravity data, and by Juno's principal investigator Scott Bolton, with the microwave data. The Great Red Spot extends at least 240 kilometers below the cloud tops. That is about 150 miles. The gravity measurements set an upper bound too. It does not go deeper than roughly 500 kilometers, around 310 miles. Put that on a map, 150 miles is farther than the distance from London to Manchester, except pointed straight down, through gas, with nothing solid anywhere along the way. Here is why that number was a shock in both directions. One camp expected the storm to be shallow, a weather feature living in the visible cloud deck, maybe a few tens of kilometers thick. It is far deeper than that. The other camp expected it to be enormous, a column reaching thousands of kilometers into the planet, anchored deep in the interior. It is far shallower than that. The Great Red Spot turned out to be neither. It sits in a strange middle zone that no model had specifically predicted, and there is an odd proportion buried in that result. The storm is roughly 10,000 miles wide and roughly 150 miles deep. That is a ratio of about 65:1, which means that despite being the most three-dimensional object in the solar system in the popular imagination, a vast churning column, the way it gets illustrated, the Great Red Spot is, geometrically speaking, a pancake, wide, flat, thin, relative to its own width. If you scaled it down to the size of a dinner plate, it would be about the thickness of a coin. It is not a hole drilled into Jupiter. It is a lens. Now the part that genuinely bothers people. On Jupiter, sunlight is absorbed near the top of the atmosphere. Water clouds are thought to sit somewhere around 50 to 100 kilometers below the cloud tops, depending on the model. That is the layer where Jupiter's weather is supposed to happen. That is where the energy is. The Great Red Spot goes past all of it. 150 miles down puts the base of that vortex well below the water clouds, in a region with no sunlight and, as far as we can tell, no obvious source of the energy needed to keep a storm this size spinning. So what is feeding it? There is no confirmed answer. Jupiter radiates more heat than it receives from the sun. Leftover heat from its formation, slowly leaking outward. And that internal heat is the leading suspect for powering the planet's weather in general. But the specific mechanism that keeps this one vortex stable, for at least 190 years, at that exact depth, remains unexplained. We now know how deep it is. We do not know why it stops where it stops. The microwave data added one more piece to that puzzle. The MWR readings showed that the storm is warmer at its base than the surrounding atmosphere at the same level, and cooler near the top. That temperature structure tells you something about how the vortex circulates internally, gas rising in some regions, sinking in others. But it does not tell you where the energy is coming from, and the papers were careful not to claim that it did. This is the part worth sitting with. 150 miles is the answer to a question we have been asking since 1665, and the answer immediately generated a harder question that we currently cannot answer at all. There is a second measurement that makes this stranger. So NO also mapped Jupiter's jet streams, those alternating bands of wind that give the planet its striped appearance. Those jets are not surface features either. Gravity data showed they extend down about 3,000 kilometers, roughly 2,000 miles, before the atmosphere becomes conductive enough that the winds are shut down. So compare the two. The jet streams, 3,000 kilometers deep. The Great Red Spot, sitting inside those jet streams, no more than 500 kilometers deep. The storm is roughly 6 times shallower than the winds it lives between. Picture a whirlpool sitting on top of a river, spinning independently, while the river runs miles deeper underneath it. That is close to what the data describes. The most famous storm in the solar system is a shallow feature riding on top of a much deeper circulation, and how those two systems interact, how the shallow vortex stays locked in place above the deep flow for centuries, is not fully explained. Meanwhile, the storm is shrinking. This part is not in dispute, because we have the drawings. In the late 1800s, observers measured the Great Red Spot at something like 40,000 kilometers across, wide enough to swallow 3 Earths side by side. Recent measurements put it near 16,000 kilometers, around 10,000 miles. It now fits about 1 Earth. It is not just narrowing. Hubble measurements have shown it becoming taller as it becomes thinner, and the winds along its outer edge have been speeding up while the interior slows. The storm is being squeezed into a rounder, tighter shape, and the outer band is spinning faster. Winds in that outer ring have been clocked in the range of 400 miles per hour, 10,000 miles wide, 150 miles deep. A storm the width of a planet, and the depth of a short flight. There is also the color, which is its own unsolved problem. Jupiter's atmosphere is mostly hydrogen and helium, both colorless. Ammonia clouds are white. Nothing in the basic chemistry accounts for a deep orange-red oval. The leading explanation is that ultraviolet light from the sun breaks apart compounds carried up from below, ammonia and hydrocarbons, like acetylene, and the products recombine into reddish molecules at the top of the storm, where the gas is lifted highest and exposed longest. Laboratory experiments have produced red-tinted compounds this way, but the exact chemistry has never been confirmed. We can measure the storm's depth to within 100 kilometers. We still cannot say with certainty why it is red. The obvious question is whether it is dying, and the honest answer is that nobody knows. The shrinking has been consistent for over a century, but the storm has also outlived every previous prediction of its collapse, and there is no reliable model that tells us what its endpoint looks like. It may dissipate, it may stabilize, as a smaller, faster, more compact vortex. Both remain on the table. And then, in October 2024, a team led by Amy Simon at NASA's Goddard Space Flight Center published something almost comic. Using Hubble, they watched the Great Red Spot continuously over 90 days, and the storm was not sitting still. It was oscillating, expanding and contracting, squeezing and relaxing, on a cycle of roughly 90 days. Simon's team described it as wobbling like gelatin. Nobody predicted that either. There is no model that accounts for a storm this size breathing on a 3-month rhythm. It was only caught because someone chose to stare at the same object, without looking away, for a full quarter of a year. Which tells you something about this entire subject. Every time we look at the Great Red Spot with a genuinely new method, gravity in 2019, microwaves in 2019, continuous monitoring in 2024, it does something we did not expect. Juno was never designed to last forever. It runs on 500 watts, in the harshest radiation environment we know of, and its instruments degrade with every pass. NASA extended the mission through September 2025, and the plan has always been the same at the end. The spacecraft is deliberately steered into Jupiter's atmosphere, where it burns up, so that it can never contaminate an ocean moon. The watching does not stop with it. Hubble's Outer Planet Monitoring Program continues to photograph Jupiter every year. NASA's Europa Clipper and the European Space Agency's JUICE mission are both en route, arriving in the early 2030s, and both will pass through the Jupiter system with instruments that did not exist when Juno launched. And there is a specific thing worth waiting for. Juno measured the storm's depth twice, at 2 moments, in 2019. That is a snapshot. Nobody has ever measured whether the depth is changing. We know the storm is getting narrower. We do not know whether it is also getting shallower, or deeper, or holding steady while the width collapses around it. Answering that requires another spacecraft, with another gravity instrument, making another pass over the same oval, years apart. That comparison has not been made. It is one of the cleanest open questions in planetary science, and it is sitting there, waiting for someone to fly it. But even when Juno goes silent, the storm does not stop. There is nothing to stop it. No coastline, no mountain range, no land. It has been turning since before the American Civil War, and it will keep turning after every person watching this is gone. 10,000 miles wide, 150 miles deep, 500 watts, and 53 days between chances to look. That is what it took to find out that the most famous storm in the solar system has a floor, and that we do not know why the floor is where it is, or what feeds the storm below the sunlight, or why it is shrinking, or why it breathes on a 90-day rhythm. We have been watching that oval since 1831. We have measured it for less than a decade. The gap between those two numbers is the whole story. If you want more of this, real missions, real published data, no exaggeration, subscribe and turn on notifications. Everything on this channel is grounded in real published research, rather than exaggerated headlines. Thanks for watching.